Okay, let's start the first Hermann Weyl lecture that we set up for the subject of mathematical physics. And this is the first lecture series we set up in honor of a non-Chinese scholar. I think Hermann Weyl is certainly great enough to be remembered in that way. Oh, there's also Emmy Noether lecture, so it's okay. One great woman mathematician and one great scholar. So Hermann Weyl, of course, is not only a very important man in mathematics, but also in physics per se. Has made fundamental contribution, especially to gauge theory. Gauge theory was started by Hermann Weyl. And we have a large number of students who are interested in mathematical physics, especially in string theory. And I think this is a good subject that many of our faculties and our students are interested in it. We probably have more theoretical physicists in our faculty than the physics department, actually. So we kind of enjoy it. And so I think it's a great opportunity for us to have Hiroshi Oguri, who I knew for a long time, to come to give the first Hermann Weyl lecture. And we know she has been in Tokyo University and went to Berkeley and then Caltech later. She has been in Caltech for more than 20 years, I think. And I have met him in Caltech and other places. And the most striking for me is his great work with Jacobi, B, Bersowski, C is Jacobi, and O is Oguri, BCOT. Oh, V, BCOV, Wafa, Conan Wafa, BCOV. So that was one of the most fundamental paper in string theory or in theoretical physics. Has great impact on the development of algebraic geometry in the subject of how to count algebraic curves of pi genus. And I think this is the only paper that has such a vast impact in the subject. Although the papers takes a long time to make it rigorous enough for mathematicians to accept, but the process of making it rigorous has been fundamentally important for algebraic geometry, and it continues to be so. It's not completely understood yet because the theory is there, but still we are supposed to use it to count all genus. But right now we can only do genus less than equal to maybe 100 or so, and so it would be nice to find a general formula to count all those genus. Well, it's a great problem still in inviting our students or our faculty to work on it. It is, as I said, has a great impact in algebraic geometry. Of course, Hiroshi has done many other things. I saw him very frequently with Conan Wafa. Their joint work has been great impact. And he has done important works in quantum gravity in many different subjects. And on top of research, he was one of the best person to explain things clearly to general layman, as we saw a few days ago, where he gave a beautiful talk on the man from 9 dimensions. Beautiful talk. And also, he was also able to explain general string theory to mathematicians much better than most physicists that I know of. So I'm very pleased to have him to come here to give this talk on Hermann Weyl lecture. So string theory and its application to mathematics and physics. Yeah.
Professor Yao, thank you very much for your very generous introduction. And I'm very much honored to be here to give the first Hermann Weyl memorial lecture. So when Professor Yao invited me to give these two sets of two lectures, I immediately accepted it. For many reasons, I love to come to Tsinghua and interact with distinguished scientists here. But also Hermann Weyl has been a very, very important and influential figure to me. And so this is actually what I read in his collected essay, Gesammelte Abhandlungen. In it, he said, beside language and music, mathematics is one of the primary manifestations of the free creative power of the human mind. And mathematics, in some sense, is a type of language, but express your idea in the most precise manner. And just like language and music is beautiful art, mathematics is also an art, as well as a very powerful tool in physics. And well, it has be beautiful music here. I don't know why, but Hermann Weyl has also been a very important person in my education. When I was an undergraduate student, I read many of his textbook. This is his book on Riemann surface and the Japanese translation. Many of his book has been translated into Japanese. Maybe you can also guess what this is. This is his Japanese translation of his book Raumzeit Materiae, or Space, Time, and Matter. And this is a book about group theory and quantum mechanics, and this is a book about classical group. And in this book about space, time, and the material, which is actually, you can see, this book is about a textbook of general relativity, but he wrote in 1918, only 3 years after Einstein published his book, his work on general relativity. And this is still one of the very good textbooks on general relativity. And I studied this when I was undergraduate student. This was not an easy textbook to study general relativity, but this was had profound influence on me. In the introduction, he said, not only in geometry, but to still a more astonishing degree in physics, has it become more and more evident that as soon as we have succeeded in unraveling fully the natural laws which govern reality, we find them to be expressive by mathematical relation of surprising simplicity and architectural perfection. It seems to me to be one of the chief objectives of mathematical instruction to develop the faculty of perceiving this simplicity and harmony. So this was sort of had a very strong impression on me that it's surprising that mathematics is so useful in natural science. Later, Wigner also wrote some essay pointing out the similar miracle of mathematics, but this is the first instance where I saw such a statement. Okay, so I was told that this set of lecture has two parts. In the first lecture, I'm supposed to give lecture for undergraduate students. So I prepared this lecture to be accessible to, at least a part of that to be accessible to undergraduate students. So I start with some general discussion about the use of mathematics in physics. And so over the last 4 centuries, since Galileo and Newton, we have gained deeper and deeper understanding of the laws of nature. And one of the ways that we have succeeded in doing that is to unify known laws of nature. So we know some part of the nature, and then we try to find connection between different laws of nature to construct more unified. Let me explain what I mean by that. So for example, before the 17th century, people knew about, well, Kepler's law was begun to be understood in the late 16th century, early 17th century. And Galileo was doing experiment in the early 17th century, which became the Newton's law of mechanics. And Newton essentially unified these laws, the theory of the motion of planet and the mechanics, that by realizing that the motion of object on the Earth, like apple falling from the tree, can be governed by the same law as that governs the motion of the moon around the Earth. So it became the law of universal gravitation. Similarly, in the early 19th century, people like Faraday began to realize that there is a connection between electricity and magnetism. Magnetism was, of course, known by Chinese like thousands of years earlier and used in many ways, like navigations. And electricity became known a little bit later. But then it was unified by Maxwell into the electromagnetism. So now we have two sets of laws, the law of gravitation and the law of electromagnetism. But then it was realized that the Maxwell's electromagnetism and Newton's mechanics was not compatible with each other. They have different symmetries. And it was Einstein who unified them into special relativity. And I wonder what this music is, but sorry? Sorry? Oh, it's a bell for students to show that they have to come to class or something. Oh, okay, good. Yeah, no problem. So they became special relativity, but then it was also Einstein also realized that the special relativity was not compatible with Newton's law of gravitation. They had a different symmetry, and so then he unified them into general relativity. So you see that with this general relativity, all known laws of classical world were unified into single consistent mathematical framework. So if that was all, then we have unified ultimate unification. So we are happy. And the rest of the work for physicists would be to derive all the natural phenomena from general relativity. But it didn't work out that way because between 1924 to 26, the quantum mechanics was discovered. In fact, the next year is officially the 100-year anniversary of quantum mechanics. And this was very different laws of nature compared to this classical law. But unification of special relativity and quantum mechanics took place relatively quickly, just a couple of years after quantum mechanics was discovered. People like Heisenberg and Pauli already wrote down the Hamiltonian for quantum electromagnetism. Although it took 20 years for the ultraviolet divergence of this theory to be resolved by renormalization. And in fact, 50 years before the standard model of particle physics was written in the language of quantum field theory. But it was relatively early. So, but then we still have the work to do to unify this quantum field theory with general relativity. But before going into that, I'd like to point out that whether it is the law of universal gravitation or electromagnetism or special relativity or general relativity or quantum field theory, they are not discovered to explain new physical phenomena. It's not like suddenly experimenter discovered a new phenomena and the theorists tried to explain it and came up with this law. No, all the phenomena were known much earlier before any of these developments took place. And they are all motivated by the work aimed at resolving contradiction between existing theory and constructing a more consistent unified theory. So this is, you see that much of this development was in some sense mathematical work, that the laws of nature were known and the task was mathematical task to unify this. So this is why theory, physics, the mathematics play such an important role in physics. It's one of the reasons why mathematics is so important, because much of this progress in unification was driven as a mathematical work. So now, what about this one? Okay. So in some sense, we have been understanding much deeper and deeper structure of nature by going into more and more microscopic world. So we have this the law of molecules, and molecules turn out to be made of atoms, and atoms are made of nucleus with electron going around it, and there is a law of nucleus and standard model. So by going to smaller and smaller space, we understand deeper and deeper structure of nature. So you can ask, well, does it go forever? Well, will it end somewhere? And if it does, where does it end? So let me tell you that, in fact, this is going to end at somewhere, and there is a theoretical reason for this. So physicists have been building this large accelerator. Right now, there is the largest accelerator in the world is near in Geneva, in the Large Hadron Collider, and but there might be even stronger one built near Beijing. And the reason we build this accelerator is that if you have more powerful accelerator, then you can see smaller structure of the world because of this relation, that the resolution of space is inversely proportional to the energy. So if the energy is bigger, the resolution of the space becomes smaller. But Einstein also pointed out that E equals mc squared. So that means that if the energy becomes large, then you have more massive object at the center of the collision, and eventually it gravitates. And then if the energy becomes big, then it can become black hole. And if the black hole is formed, then the size of the object becomes proportional to the mass. So before gravitation was important, the resolution was inversely proportional to mass. But once you take into account gravity, there is another possibility that the resolution can be proportional to the mass. And this is dictated by the size of the event horizon of the black hole. So that means that the resolution of the accelerator is actually maximum of these two terms, and the maximum is bounded below by this constant, which is given by Newton's constant, Planck constant, and speed of light. This is called Planck length. So that means that even if you build arbitrarily powerful accelerator, you cannot resolve the space smaller than this Planck scale. And in physics, we think that if there is no way, even in principle, to observe certain phenomena, then we don't regard such object phenomena to take place. So we say that we cannot prove phenomena shorter than this scale. So from this kind of argument, we see that even though for the last 400 years, we have been discovering more and more fundamental laws of nature, but once we get to the unification of general relativity and quantum mechanics, that is the most fundamental laws of nature, that our historical march toward more fundamental laws of nature will terminate at the Planck scale. So we can regard, therefore, this to be the ultimate unification, as far as I know, and that's why it's very interesting. And it's surprising that we already know a good candidate to unify general relativity and quantum mechanics, and that is string theory. Of course, this theory has not been experimentally verified, but this is the only laws of nature that we know of that unifies everything here. So it's very worthwhile to study this theory. So in this theory, we postulate that fundamental building blocks are not point particles, but strings. And it is defined in 9 space and 1 dimension. So that's the name. That's why I made this movie called The Man from 9 Dimensions, which showed in the last weekend. But we live in 3 dimensions. So this extra 6 dimension is compactified on the space called Calabi-Yau manifold. And this is a beautiful space. And in particular, if we use this space, then we can actually have a way of explaining the number of elementary particles and the forces between them, and Higgs boson that sort of breaks the symmetry to explain the mass hierarchy. And all these structure emerges from the geometry of Calabi-Yau manifold. So one way for physicists to try to connect string theory to our observed world of elementary particles is to derive quantitative prediction of physics from the geometry of Calabi-Yau manifold. So studying geometry of Calabi-Yau is very important for physics for this reason. But our understanding of this geometry is still very limited. There are lots of things we need to do. For example, we don't even know the metric on the Calabi-Yau manifold. So if we don't know that, how can we sort of do useful calculation? So that's where the method of topology becomes useful. We can actually do lots of useful calculation using geometry of Calabi-Yau without knowing metric. Of course, there is an important development in constructing metric explicitly. Professor Yao's proof showed that metric exists in principle, but it's one thing to prove that metric exists, and it's another to actually construct it. And but we can try to do two things in such a situation. One is actually to develop method to actually construct metric explicitly, and another is try to do useful calculation without knowing metric. So we can go both ways. So today I will tell you the second method, which is to actually do useful calculation without knowing the metric explicitly. And that's the idea of the use of topology. So here is the first instance where the idea of topology was useful. And it is in the paper by Candelas, Horowitz, Strominger, Witten, appeared in publication in 1985, although preprint appeared a year before 1984 in December. And so this paper had a big influence on me. And in fact, this is also the paper where the word Calabi-Yau manifold first appeared in scientific literature. And one thing they showed was, so basically start from 10 dimension using Calabi-Yau manifold, how you can sort of see the structure of standard model of particle physics with 17 particles like that. And as you can see, so if you have learned the elementary particle theory, we know that in standard models, there is a 3 generation of particles. So 2 quarks and then 1 electron and neutrino. This set of 4 particles makes 1 generation. And there are 3 generations of elementary particles. And in this paper, they related this number of quark species to the Euler characteristic of Calabi-Yau manifold, which is a topological information. So this is a sort of example where without doing some explicit metric calculation, we can actually deduce the number of quark species, which is an important feature of standard model, from the topological feature of Calabi-Yau manifold. Okay, and then from this, people also started to discover a very important symmetry of Calabi-Yau geometry called mirror symmetry. And I'll tell you a little bit more about this. But it relates the complex structure and scalar structure of Calabi-Yau manifold in a deep way. And this distribution of non-Calabi-Yau exhibit mirror symmetry, which exchanges H11 and H21. Now, so this was so inspiring to me. So I started to study some of this, and it actually led to my PhD thesis. So today, my lecture today is for broad audience. So I will cover some of my work for the last 35 years. And tomorrow, it's supposed to be more technical talk. So I'll tell you my work in the last 1 year. But today I'll talk about some of my old work too. And one of my oldest work is my PhD thesis. So in my PhD thesis, I was so impressed by this relation between Euler characteristic on Calabi-Yau and quantum species. So I consider generalization of this idea called the elliptic genus, which is a string theoretical generalization of Euler characteristic. And this idea of this concept of elliptic genus turned out to combine various interesting concepts in mathematics, and as I will explain, and one of which is a mock theta function. So in 1987, before I got my PhD, I was invited to give some talk at the winter school in India. And this turned out to be the centennial of Ramanujan's birthday. So Freeman Dyson was there, and he gave a very interesting speech, which you can read in the proceeding, and in which he said that mock theta function give us tantalizing hint of grand synthesis still to be discovered. My dream is that I will live to see the day when our young physicists struggling to bring the prediction of superstring theory into correspondence with the fact of nature will be led to enlarge their analytic machinery to include mock theta function. Okay, so we are still struggling to bring prediction of superstring theory into correspondence with the fact of nature. But in fact, his expectation that mock theta function should become useful in string theory actually happened much earlier than he expected. In fact, just when Freeman Dyson was making this speech, my advisor, Toru Eguchi, and his collaborator, Anne Taormina, was writing a very interesting set of paper studying representation of superconformal symmetry on string worldsheet. And this symmetry is very important in studying string theory propagating in Calabi-Yau manifold. When you have Calabi-Yau manifold, and when string is propagating on the Calabi-Yau manifold, on the worldsheet of string theory, there is a particular symmetry called superconformal symmetry. So Eguchi and Taormina studied the representation theory of this symmetry and discovered that in the character of this algebra, mock theta function appear. So in my PhD thesis, I studied elliptic genus of K3, which is a generalization of Euler characteristic. Basically, you consider A hat genus and Chang character of some tensor product of tangent bundle and sum over this series over K3. And if you consider this particular summation, it becomes a nice modular form. And so this is called the elliptic genus. And one of the things I did in my PhD thesis, which is 35 years ago, is to expand this elliptic genus in character of n equal 4 superconformal algebra. And I found the following interesting observation. First of all, by just knowing the modular invariance, the coefficient of this is fixed to be 20, which is actually related to H11 of K3 surface, and therefore also Euler characteristic of K3 surface. So without doing geometric calculation, by knowing modular invariance and the representation theory of symmetry, you can actually deduce the Euler characteristic of K3, which I thought was interesting. And then I started expanding this elliptic genus to the higher order in this Q expansion and found all these interesting series of numbers. So these correspond to particular characteristic class calculations over here. But I thought that these numbers must have some meaning too. But in my PhD thesis, I couldn't figure out a reason, so I just left it like that. But then 20 years afterwards, I realized that, well, if I had actually divided this number by 2, then all these numbers have meaning, that they are all dimensions of irreducible representation of Massieu group. So Massieu group is M24 is one of the largest series of sporadic finite simple group called the Massieu group, which was discovered in 19th century, and used in many important things, like, for example, the error correcting code called Gore code, which was used for Voyager to send data from planetary exploration. And so the Massieu group is a very, very interesting and deep group. And it turns out that through the elliptic genus, there is actually a deep connection between the Massieu group and mock modular form and Calabi-Yau geometry. So this became actually a very interesting part of activity in the finite group and the moonshine series. And so it turned out that my PhD thesis has some long-lasting interest in this area. A few years ago, I visited Cambridge University and went to the Wren Library, and David Tong kindly showed us the original manuscript of Ramanujan that he sent to Hardy in his last year, where we can see some of the mock theta function formula that actually I used in my PhD thesis. So it was very nice to see that. And the elliptic genus is useful for many other things. For example, this is my paper with Christoph Keller, who was a postdoc at Caltech. And there, actually, I applied the elliptic genus not for K3, but Calabi-Yau threefold. And there, we found that there is actually a very interesting inequality that we can derive between the spectrum of conformal field theory, whose target space is Calabi-Yau, and Hodge number. And there is some kind of phase transition that takes place when the Hodge number becomes 493. And if Hodge number exceeds 493, there must be some particularly low-lying spectra, state in the spectrum. And so there seems to be qualitative difference between Calabi-Yau manifold of Hodge number below and above this. And this is actually an interesting region of Calabi-Yau, because there have been a lot of classification of Calabi-Yau manifold, in particular like weighted over homogeneous space. And it was found that there is actually a sort of upper bound for the Hodge number of Calabi-Yau, and it is about this area. So there might be something more interesting to come out from this. So this was sort of one of my initial attempt to apply topological method to study Calabi-Yau manifold. But as Professor Yao pointed out, that some of my work also involves topological string. So I'd like to tell you a little bit about this approach. So just briefly about string theory in general. So if you have point particle, well, so the particle is a point-like object without size. So when you send particle from point X to Y in space, it's going to make one-dimensional trajectory. If you send string from one point to another, then it makes two-dimensional surface called worldsheet. And one of the interesting features of string theory is that this procedure automatically incorporates interactions. So if you have 4 points, you can still connect it by smooth two-dimensional geometry. Although, on the other hand, if you have point particle, in order to connect 3 or 4 points, you need to introduce vertex, which is a new structure. But in string theory, interactions are automatically included in the definition of theory. So once you define this type of what the spectrum of the theory is, then you automatically already know the interaction too. So this is sort of a very nice feature of string theory. You can also consider as two-dimensional worldsheet to connect incoming state to outgoing state in this way too. So this is sort of a caricature of string theory, but we can also try to formulate string theory more precisely in the following way. Now, first we start with two-dimensional conformal field theory. So let me try to define string theory a little bit more precisely, because I think there are some mathematics undergraduate students here too. So let's start with two-dimensional conformal field theory. And one of the definitions of conformal field theory includes Hilbert space, which can be expanded into sum of product of irreducible highest weight representation of Virasoro algebra. So here is a Virasoro algebra, and C is a central charge which is constant for given conformal field theory. And the VH and the VH vars are representation of this algebra, highest weight representation with an H is the highest weight. And N is a multiplicity here. And so this is a Hilbert space. And once you have a Hilbert space, then you can define conformal field theory as a functor. Namely that for each Riemann surface with a set of N incoming boundary and M outgoing boundary, you can define a map of the Hilbert space of conformal field theory, N tensor product of Hilbert space to M tensor product of Hilbert space. And so you can define this functor, and if this functor obeys certain set of axioms, which in view of time, I don't have time to explain this detail, but it's very well spelled out set of axioms, then you can actually define two-dimensional conformal field theory in this way. Okay? Now, if once you have this conformal field theory, some student raised hand, I don't know why. Should I respond or what should I do? I can ignore it. Okay, very good. Once you have this definition of string conformal field theory, then you can actually make use of this string theory to define, make use of conformal field theory to define string theory. So the definition of string theory goes as follows. So you also use this functor, but you actually, in order to define string theory, you need a measure. You need you need to integrate this quantity over moduli space of Riemann surface. So you need this functor, but it's also the measure on the moduli space. And one of the requirements of this measure is such that it satisfies this equation. So let me explain this equation. So this omega is the volume form, the measure on the moduli space. And you can consider acting exterior derivative on it. But in addition, you have this operator Q acting on the Hilbert space so that it's squared to be 0. And the Virasoro algebra of this conformal field theory is given by commutator of Q with something else. So once you have this structure, then you can define string theory. Okay? So you can see that this implies various conditions on conformal field theory. But one of which is that if you require that Virasoro algebra to be expressed as anti-commutator with this Q operator, which is nilpotent, then the central charge of Ln has to be equal to 0. So you have to arrange conformal field theory so that total central charge is equal to 0, and with this Q in it. And once you have this, then you can ask whether you can solve this equation. And once you have a way of solving this equation and construct omega, then you can define string theory. So whenever you have this, you can have string theory. So topological string is one of the ways to construct such a measure. So in particular, Calabi-Yau threefold, the Calabi-Yau manifold with 3 complex dimensions, is particularly interesting case in this, because in that case, we can define this measure where there are no boundaries. So you can define what physicists call partition function for given genus, for closed Riemann surface of given genus. So this is sort of the definition of topological string amplitude. You use this definition to define the measure of a moduli space of Riemann surface and integrate that to get some number. And this is genus G topological string amplitude. And Professor Yau's theorem says that if M is scalar with trivial canonical bundle, the rich flat metric is uniquely determined by scalar class and complex structure. And in string theory, it is natural to complexify scalar moduli. So that means that this topological string amplitude is also a function of complex structure and complexified scalar class of the Calabi-Yau manifold. In fact, so this is what one of the things I did in this paper with Bersharsky, Sergio Cecotti, myself, and Cameron Buffer that Professor Yau generously mentioned in his introduction. There are 2 types of Calabi-Yau, 2 types of topological string theory. In one type called A model, it depends only on the scalar structure, and it counts the number of the way that a Riemann surface can be mapped into Calabi-Yau manifold in a holomorphic fashion. And there is another model called the B model, which is related to the quantization of complex structure of the moduli space of Calabi-Yau in the way that I will discuss a little bit more later. So there are 2 types of models. A model is give you Gromov-Witten invariant, and B model gives you quantization of complex structure of Calabi-Yau manifold. So let me give you an example of the calculation in genus 1 case. So this is the long formula, but in the case of genus 1, topological string amplitude, for example, by expanding this appropriately in terms of scalar moduli, then you can extract this number n, which is related to the Gromov-Witten invariant, which count the number of holomorphic map from genus 1 surface and genus 0 surface in this case, into Calabi-Yau manifold. And on the other hand, if you have B model, then the topological string amplitude is given by calculation of determinant of Laplacian on the Calabi-Yau manifold. Now, there is this notion, as I mentioned earlier, called mirror symmetry, which exchanges basically the complex structure and the Kähler structure, namely exchanges the A model and B model. So if you use mirror symmetry, you can relate this calculation of Gromov-Witte invariant to the calculation of determinant of Laplacian. So this is a very useful thing. So because if you use mirror symmetry, you can relate the two seemingly different calculations. One is a counting of holomorphic map, and one is a quantization of complex structure. So in the case of genus 1, so for example, if you have mirror pair of Calabi-Yau manifold, you can equate the genus 1 topological string amplitude for A model to genus 1 topological amplitude of the mirror of that Calabi-Yau manifold, and relate this number to the calculation of determinant of Laplacian. So as I said, this formula comes from the topological string calculation that I formulated with Sergio and my collaborator. But mathematician can regard that as a conjecture. And in fact, it was rather ill-formulated conjecture at the time. But thanks to the work by mathematicians like Zinger, this has been made more precise, and in some cases was actually verified in a mathematical rigorous fashion. So in higher genus, it's much more deeper. And in higher genus amplitude, these are also related to Gromov-Witte invariant. But in the case of B model, it's related to some deep theory called 02 theory. And in fact, Professor C.B. and Kevin Costello have very deep mathematical work in formulating what precisely is a B model to do this calculation. So now, so this is a formal theory. So in principle, if we can calculate this topological string amplitude, then we can deduce this number. But it's one thing to formulate it, but it's another thing to actually calculating them explicitly. And there are various useful methods to calculate it, and one of which is called holomorphic anomaly equation. As I said earlier, this topological string amplitude is defined as an integral over moduli space of Riemann surface, and measure satisfies this equation, that D is the exterior derivative and Q is an operator in the conformal field theory, which also nilpotent. So both D and Q are nilpotent operator. So you can think of this as some kind of boundary operator. So you have a closed form which you integrate over moduli space. Now, the Q invariance can be regarded as holomorphicity on the Calabi-Yau moduli space. So this equation shows that this f of g is essentially holomorphic quantity. In the A model case, it's holomorphic in Kähler moduli. In the B model case, it's holomorphic in complex moduli space. But if omega is annihilated by Q only, it means that it's actually exactly holomorphic. But the equation is actually D plus Q is acting omega is equal to 0. So that means that there is a possibility that holomorphicity is broken at the boundary of the moduli space of Riemann surface. And this is exactly what happens. And this is what Sergio and I and others showed in this BCOB paper, that because of this boundary effect, there is actually a much more interesting equation called holomorphic anomaly equation. And this equation is very interesting because this is a recursive equation with respect to genus. So in principle, if you can integrate this equation, once you know genus 0 and genus 1 answer, then you can recursively determine higher genus. So in fact, in my paper with Sergio and the collaborator, we have done this integration for the first couple of genus, genus 2, etc. But to go for higher and higher genus, we need to understand better and better about the behavior of f of g near the boundary of the moduli space. And it was actually estimated by Albrecht Frame and the collaborator that in certain compact Calabi-Yau manifold, we can continue this procedure up to genus 51. But beyond 51, you need to provide more data to be able to do that. And so it's actually desirable to complete this procedure. So anyway, so this was a very satisfactory work. And a few years ago, we had this 25th anniversary of this BCO paper where Professor Yao kindly came to celebrate this occasion. Now, there are also very interesting connection between this type of topological string calculation with Largian duality, which is another very deep subject in mathematical physics. Largian duality is an idea that certain calculation in gauge theory is related to calculation in gravity. More broadly, certain calculation in open string theory is related to closed string theory. So very famous ADS-CFT correspondence is an example of this Largian duality, that it's a duality between gauge theory and gravity. But you can also consider analog of this Largian duality in the context of topological string and do many interesting calculations. So in string theory, open string are described in terms of D-branes. So open string means that on the worldsheet there are boundaries, and the boundary condition physicists call as D-branes. And then there are a state in open string. So previously we considered, in order to define string theory, we introduced conformal field theory and consider conformal field theory state for each of these closed surfaces. But in order to define open string, we need to consider a conformal field theory state attached to open segment. Then we need to introduce boundary conditions. So in some sense, open string theory can be regarded as morphism between the boundary conditions. So now suppose you have closed string, then you consider map from Riemann's closed Riemann surface to Calabi-Yau manifold. But when you have open string, what you have is that you need to, in addition to closed Riemann surface, you have to introduce boundaries. So that means that you have to color Calabi-Yau manifold to introduce some boundary conditions. And these are called D-branes. So now, if you have a topological string with a boundary condition, that means that in addition to genus, you have to specify the number of boundaries. And for each boundaries, you need to specify the type of boundary conditions. So that means that the topological string amplitude can be parameterized by genus and the number of boundary for each type of boundary conditions. So from this, you can define generating function of this boundary condition. For each boundaries, you can introduce some kind of parameters, weight them, and sum them up to define this amplitude. So there is this Largian, so in this context, Largian duality can be formulated as the following conjecture. So suppose you have this open string amplitude and consider generating function of boundaries by introducing fugacity parameter for each of these boundary conditions, sum them. And then you get some kind of a function which depends on genus and parameter. And the conjecture is that for each such function, there is a family of target space such that this can be regarded as closed string amplitude on such a family of target space. So this is a closed open duality. So here's an example. And this is an example that Gopakuma, Baffa, and myself worked out 20 years ago, which is the following example. So suppose you consider open topological string amplitude, but in a very special case, which is a cotangent space of three-dimensional sphere. And you consider D-brane wrapping on this base 3 sphere. It was actually shown by Ed Witten that this topological string theory is equivalent to Chan-Simon theory defined on S3. But because this is topological string theory, so in this theory, we can actually consider Paschen function which depends on genus and number of boundary which end on the base of S3. Now we can actually consider generating function of this Paschen function by introducing this parameter Tn. And what we found is very interesting that you can actually do this summation and the coefficients are now related to actually Chern class of Hodge bundle over closed Riemann surface moduli space, and also Euler characteristic of closed moduli space of Riemann surface. So this is actually sort of example of open-closed duality or Largian duality in a very, very simple setup. And in fact, you can regard this expression as closed topological string theory on the resolved coniform. So you can relate open topological string theory on cotangent space on a 3-sphere to closed topological string theory on the resolved coniform. So this is, you can regard this as a simple version of open-closed duality. And in fact, many features of this duality is closely related to the ADS CFT correspondence. So you can think of this as a toy version of string theory, the ADS CFT correspondence. You can also introduce Wilson loops in this game, and then relate the closed-string interpretation of knot invariant. And this is actually some of the formula we derived was derived by Kefen Liu and his collaborator. There is actually similar version of this open-closed duality worked out by Robert Digraph and Qumran, which relate the matrix model, which is also a version of open string theory, to closed string theory on the spectral curve of this matrix model. So this is another relation between the closed topological string and open topological string. And there are many applications. So this way that the topological string is related to many different aspects of mathematics, matrix model, and Chern-Simon series. And all these are sort of unified in the framework of topological string theory on Calabi-Yau manifold. But you can also apply this to physics questions. And one of the important problems in physics is count the number of physical states. And you can use topological string to count the number of physical states. And so this was actually my work with Andy Strominger and Cameron Buffer. It's called OSB conjecture, in which we have provided a formula to count the number of bound state of D-brane on Calabi-Yau manifold using topological string amplitude. And again, there is a open string version of a similar formula, which is related to the Kovanov cohomology. Now, like Professor Yao said, so right now we have very limited tool to calculate topological string amplitude, and the best we can do is up to go to genus 51. And it's desirable to go to even higher genus. And especially, I think it's important to develop tools to understand the compact Calabi-Yau manifold. There are already some very interesting tools to calculate topological string amplitude for all genus for non-compact Calabi-Yau manifolds. For example, if you have toric Calabi-Yau, there is an idea called topological vertex, which you can use to calculate the toric Calabi-Yau topological string amplitude to all order. But for compact Calabi-Yau, it's very important. But it's very important to understand counting of topological string for compact Calabi-Yau. For example, in test, in order to actually check against the OSB conjecture, you need to understand compact Calabi-Yau. But compact problem is, of course, much more difficult than non-compact Calabi-Yau. But there have been actually lots of interesting development. In fact, the idea of resurgence can be very promising. And there can be some important development in this area in the near future. So I think this is one of the very interesting directions in topological string to explore. So I only have 5 more minutes. So let me briefly give you a preview of what I'm going to do tomorrow. Okay. So so tomorrow I'd like to discuss a more recent series of development, which is actually the relation between the geometry and the information. So one of the ways that this appeared was in the context of ADS CFT correspondence, where Liu and Takayanagi pointed out that entanglement entropy, which is sort of von Neumann entropy between the different regions of conformal field theory, is given by minimum surface in anti-Noether space. So it's a very interesting formula which relate the entanglement entropy, which is an information theoretical quantity in quantum field theory, to purely geometric quantity to measure the area of minimum surface. And this shows some very special property of entanglement property in quantum field theory. And in fact, in my work with Nimbao, Stefan Nezami, and Sally, so Michael Walter, so this is a sort of collaboration between string theorists and quantum information theorists, show that there are actually very interesting entanglement properties of this entanglement entropy when you have a holographic dual. And this can be captured in the notion of called holographic entropy cone. If you have entanglement entropy, there are various inequality nodes, and this is one of the famous ones proven by Elliott Lieb, for example, called strong subadditivity conditions. And but it turns out that in the context of ADS-CFT, Yu-Takayanagi formula satisfies large family of inequalities, and now we formulated this as holographic entanglement entropy cone. And one of the distinct feature of the holographic entanglement is its deep relation to quantum error correcting code. I guess this music means that I should stop very soon. So I'll stop. I'm wrapping it now. So this quantum error correcting property, or maybe I'll discuss this more tomorrow. But the way that the ADS-CFT correspondence works is very deeply connected to the fact that Ryu-Takayanagi formula is related to the quantum error correcting code in quantum information theory. And Daniel Harlan used this property to prove that quantum gravity in anti-Utah space has no global symmetry. So I will discuss more about it tomorrow. So anyway, so my main message to you today is that this kind of idea developed in physics, and especially trying to understand unification of different ideas in physics, often have unintended application. And that application can be in mathematics, but also in physics. And so I think that this is a very, very promising direction to pursue both in mathematics and physics. So I would like to end this lecture with another quote from Round Site Materially from this textbook by Hermann Weyl. And he said that the Greeks made space the subject matter of a science of supreme simplicity and certainty. Geometry became one of the most powerful expressions of that sovereignty of the intellect, and it was the highest ideal of every scientist to carry on his science more geometrical. More geometrical. I think this is a word, thank you very much, more geometrical. So this is actually a word that appears in Spinoza's Ethica. I think that Spinoza regarded geometry so important. He was inspired by Descartes. So he actually wanted to deduce ethical idea from geometric means. And that's what he called more geometrical. And but I think this more geometrical is very, very powerful in physics too. So I think that studying geometry can be very useful on its own, but also have very big importance in physics too. So that's my message. Thank you very much for your attention.
It's a great speech. So, any questions to the speaker? Yeah.
Hello, Professor Oguri. I think it's a great talk, and I wonder how you combine the mystery numbers in your PhD thesis to the theory of group representation.
Yeah, so this is actually a very interesting story. So you asked me about this is actually one of my favorite piece of work.
How you manage to divide by two?
So as I said, I wrote this down this number in my PhD thesis, and I even at that time I had some impression that there is some deep connection of this type of calculation to Massieu group, and the reason was that I was actually after I became I got my PhD. I became associate professor at RIMS, Research Institute for Mathematical Science in Kyoto University. And there was a Professor Mukai. And Mukai studied some very interesting fact about K3, that he showed that what kind of automorphism that the K3 surface can have. And he said that biggest you can have is M23. So somehow there was some idea that the Massieu group has something to do with geometry of K3 surface. And so, but M32 is not the biggest Massieu group. So I was speculating even at that time that somehow string theory must enhance symmetry. So in string theory calculation like elliptic genus, somehow there must be M24 playing a role. But I couldn't find a way to relate M24 to this type of calculation. And then, so one day I was in Aspen Center for Physics and discussing with Toru Eguchi and Yuji Tachikawa about my favorite subject, what are these numbers? And Yuji said that, well, if you want to relate it to M24, why don't you check the character table? And I should have done this 24 years ago, but at that time, actually, I had this Encyclopedia of Mathematica on my laptop. So I opened the character table of M24. And at the beginning, we couldn't quite figure out the relation because these numbers there are these numbers in the character table. And then we realized that, well, this is actually half of these numbers. so for 22 years, I couldn't figure out how to divide by factor 2. And but then it's all fell into pieces. And now it has actually proven by mathematicians like John Duncan. And they actually showed that not only the first few number, but in all order in this Q expansion, these are all combination of dimensional representation. In fact, you can twist this elliptic genus. You can actually define the action of Massieu group M24 on this elliptic genus, and extend it to the character of M24. So you can define M24 character valued elliptic genus, and then you can actually do this decomposition into reducible representation uniquely. So there are lots of interesting structures, but we still don't know. So this is actually, this is not completely resolved it in a satisfactory way, because we still don't know why there is action of M24 on the elliptic cohomology of K3. We do know that if we calculate the elliptic genus, somehow all these counting fall into representation of M24. But that means that on the elliptic cohomology, there must be action of M24. And we don't have the construction of this. You know that there is a very famous Massieu, not Massieu moonshine, so there is a famous monster moonshine. So this was also observed accidentally, that people looked at what's called modular J function and expanded, did a similar Q expansion, and found that all these coefficients are dimensional representation of the monster group. So this was observed in late 1970s, but it took like 15 years or so before Borchardt actually gave explicit construction of action of monster group on this space. And I think we need to have analog of this Borchardt construction for elliptic cohomology of K3 in order to understand this structure fully. This actually would be a very interesting question. Thank you for your question.
Thank you very much. It's a miracle.
Mm-hmm.
Okay, other.
Yeah, I can't remember this, but the deformed conical, topological A string on deformed conical. What is the mirror for the deformed conical?
So let's see. So here, so in this example, So let's see. So let me try to understand the question. So we are talking about the mirror symmetry.
Yeah, the open close. So you discussing
Also in the open closed duality.
Right. So T star S3, that's also
Yeah. So
Falabi-Yau.
here I showed that open topological string theory on this. You can think of this as deformed conifold.
Yes.
So deformed conifold is related to resolved conifold in this case. But
Sure.
this is not mirror symmetry. This is a
Sure,
large
sure.
N duality.
So is there mirror symmetry work on this part, like open topological, this A string, right, on T star S3?
Yeah. So this is A string, and so you can think of this as a mirror symmetry between A string, and so B version of this is matrix model. So you can think of so you can think of this as A string version of open closed duality, which relates Chern-Simon theory to closed topological. And you can ask, well, what the dual of this? Namely, that what happens if you start with resolved conifold and go to deformed conifold? And what you have is a relation between matrix theory, matrix model, and this Calabi-Yau over spectral color.
So in the B model, what is the target space that?
So in B model case, so the analog of this is that you start with the deformed, let me see, resolved conifold. So in the resolved conifold, there is S2, and you can wrap now D2 brane on S2, and you can show that open string in that case is actually matrix model. So in that case, it's actually Gaussian matrix. And then you can actually relate that to closed string on the deformed conifold. So there is actually a mirror version of this.
Okay, thanks.
Okay.
Yeah. Other questions? Yeah.
Oh, good to see you.
Yeah, thanks very much for the wonderful lecture. I think the question is maybe a bit vague. So in this connection between entanglement and the space-time, do you think supersymmetry plays a conceptually essential role, or is it like a tool for us to do computation?
Yeah, so that's a very, very interesting question. So in this what's called the entanglement wedge reconstruction, which relate the quantum error correcting code to holographic reconstruction, we do not explicitly make use of supersymmetry. However, all known examples of ADS-CFTs are supersymmetric. And in fact, Kumran Buff and I even have a conjecture that there are no non-supersymmetric ADS-CFT correspondence. So I do not know. It's a very interesting, deep question whether supersymmetry any plays a role in this, not directly in this type of construction. And in fact, in many toy models like spin network model that Janet Huang is working, for example, there is no explicit use of supersymmetry. But yeah, but I do not know. There might be some deep connection. Thank you for asking.
Other questions? Okay, so if there's no question, let's end.
Thank you. Thank you very much.